Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, this is our first lecture of the course. The course name of your course is Waves and Optics. This is your course for your semester 4. You know, there is a 4-credit course. 4-credit course. That means your theory paper will have maximum marks of 60. As you know, 1 credit is 15 marks in case of theory. I have already shared syllabus with you in the WhatsApp group. You have 4 units in the syllabus. Unit first, then there is unit second, then we have unit third, unit 4. Unit first is about superposition of oscillations and some general properties of wave motion. Unit second is about optics, like interferences discussed in the unit second and other related phenomena. Unit third is about diffraction and other related properties, and unit 4 is mainly about sound. You know, sound is also a wave, is a longitudinal wave, so it's about that. So you need to go through the syllabus. So we'll start with unit first today. So let us start. In unit first, we need first the knowledge of the simple harmonic motion. So I will refresh your memory. You have gone through this concept of simple harmonic oscillator in your previous classes, but I will first introduce that so that I can move forward in the syllabus. So today in this lecture, we will discuss the simple harmonic oscillator. The simple harmonic oscillator. First, as you know, oscillation is a to and fro motion. You can have many examples of oscillations in nature. For example, if we connect some mass M, this is my mass M and this is spring. You connect one end of the spring with mass M, other end to the wall. If you stretch or compress the spring by moving this mass this way or this way, what will happen? This mass will begin to oscillate. So this to and fro motion is an example of oscillation or oscillatory motion. So in oscillation, there are three positions of importance. One is mean position, and there are two extreme positions. And there are certain parameters or certain physical quantities related to any oscillation. As you know, we talk of period of the oscillation, we denote by T. We talk of frequency, we denote by nu. We talk of angular frequency omega, and there are other properties as we will see when we go through this course. There can be another oscillatory motion. You're familiar with the motion of a pendulum. This is pendulum. So it is just a simple pendulum in which we have a bulb, spherical bulb, connected with a piece of string. If you displace it, then what will happen? It will begin to oscillate. It will have mean position and two extreme positions. It will oscillate under the action of gravity. You know that. So it is also an example of oscillation. There can be many different kinds of oscillators. Similarly, you can have in some solid, in some crystal, you can have an atom vibrating about its lattice point. So that is also the example of an oscillation. Now all these oscillations we can handle through the knowledge of simple harmonic oscillator. How? Because all kinds of oscillations, it is important, all kinds of oscillations for small amplitudes are like simple harmonic oscillator. So simple harmonic oscillator is a model oscillator. It is a model oscillator in oscillations. So we developed this model because it helps us to understand other oscillations in terms of the model. And what is important, that all oscillations in nature, when considered for small amplitudes, behave or match simple harmonic oscillator, right? So we develop ideas for model oscillator, simple harmonic oscillator. Then we use those ideas for all oscillations for small amplitudes, right? So let us give definition and certain properties related to this model oscillator, simple harmonic oscillator. So consider an, I will use another color. Consider an oscillating system consisting of a particle subject to a force given by f of x is equal to minus kx. Let me name this equation first, in which k is a constant, and x is the displacement of the particle from its equilibrium position. Right? Such an oscillating system is called a simple harmonic oscillator. So this is a definition. So if we have an oscillating system consisting of a particle subject to a force given by f of x is equal to kx, in which k is a constant and x is the displacement of the particle from its equilibrium position, this oscillating system is by definition the simple harmonic oscillator. You can see, and its motion is called simple harmonic motion. The potential energy corresponding to this force is the potential energy corresponding to this force is U of x is equal to half kx square. So let me name it equation second and encircle it. You know the force and potential energy are related by this equation. F of x is the negative of the derivative of potential energy with position x. So if you differentiate this potential energy given by equation 2, negative times of that will be this force. So whether you define the simple harmonic oscillator in terms of this force or in terms of this potential energy half kx square, is one and the same thing. They are equivalent, right? As indicated in equation 1, and let me draw a figure first, then we will understand it. You can draw a figure with me. We complete the figure first. I'll use another color here. Another color. It means another color. I will use another color here. Let me name this figure 1. First one is part A, second one is part B. I will check the figure, then I will explain it. Okay, that's okay. Let us move. So we have defined simple harmonic oscillator as an oscillating system consisting of a particle subject to this kind of force given by equation 1, or equivalently having potential energy of the form given by equation 2, g of x is half kx square. X is what? X is the displacement of the particle from its equilibrium position, and k is constant. So as you can see, as indicated in equation 1 and plotted in figure 1, A, this one, the force acting on the particle is directly proportional to the displacement, but is opposite to it in direction. As you can see, this equation, force is directly proportional to displacement, but since there is negative sign here, so it is oppositely directed to it. That means if you double the displacement, force experienced by the oscillator will double. If you triple it, it will triple. If you half it, force will be halved because it is directly proportional, but simultaneously it is also oppositely directed to displacement. That means if the oscillator moves to the right, force will be to the left. If oscillator moves to the left, force will be to the right. In other words, if oscillator goes in positive x direction, force will be pointing towards negative x direction. As shown in this figure 1a, This is the plot of f of x versus x. You can see it's a straight line because force is directly proportional to displacement, but it's oppositely directed to displacement. That means when x is positive, force is negative. When x is negative, force is positive. As you can see in the graph, on this region, you have positive side of the x-axis. This is origin, so force values are negative. And on left side, x is negative, but force is positive. This is the meaning of force being oppositely directed to the displacement. And mass m is shown at an arbitrary position x in this diagram from equilibrium position. O is the equilibrium position. At equilibrium position, displacement is 0, so x is 0, force is also 0. When displacement from the mean position or equilibrium position is 0, particle is at equilibrium position, force is 0. So this origin here is equilibrium position or mean position of the oscillator. So you can see this particle having mass m at this position shown is at positive x, so force on it will be towards negative x direction because force is oppositely directed to displacement, right? Then what is plus xm and minus xm? These are two extreme positions. Plus xm is the maximum displacement on positive side, and minus xm is the maximum displacement of the oscillator on negative side of x-axis. So oscillator moves along the x-axis between extreme positions minus xm and plus xm, right? This subscript m stands for simply maximum value of x. So plus xm is the maximum value of x attained by the oscillator on positive side of x-axis, and minus xm is the maximum value of the x coordinate attained on negative axis, right? And this is figure 1b shows what? It shows how potential energy varies with position of the oscillator. As you can see, this potential energy is proportional to square of the displacement from mean position, so graph is parabolic. This curve is u of x. So at mean position, you can see potential energy is 0. And this horizontal line shows E, total energy. Total energy of this oscillator is constant throughout the motion, as we will discuss, or as you might be knowing for simple harmonic oscillator, right? So potential energy varies as square of the displacement, and force versus displacement is linear. So this is the definition of simple harmonic oscillator, and the motion of this oscillator is simple harmonic motion, right? So let's move forward. You might have recognized these equations 1 and 2. They are simply the expressions for the force and potential energy of an ideal spring of force constant K compressed or extended by a distance x, right? Hence, a body, let me write it, as I repeat, I'm telling you this expression for force and this expression for potential energy are simply the expressions for the force and potential energy of an ideal spring of force constant K compressed or extended by a distance x. Hence, a body of mass m attached to an ideal spring of force constant k and free to move over a frictionless horizontal surface is an example of a simple harmonic oscillator, right? I repeat, a body of mass m attached to an ideal spring of force constant k and free to move over a frictionless horizontal surface is an example of a simple harmonic oscillator. I will show this in figure. Let me draw a figure first. I will use some other color. Complete the figure first. Let me use another color here. This is rigid, relaxed, compressed, this is relaxed, and complete the figure first. This is our figure 2. So it is a simple harmonic oscillator consisting of a spring acting on a body that slides on a frictionless horizontal surface. Let me complete the figure. Then I will explain. F is minus k xm. Acceleration is minus am. V is 0. Force is pointing this way. Here F is 0, A is 0, V is minus Vm. Here this is F. Here F is plus K xm. A is plus AM. V is 0. Here F is 0. A is 0. V is plus Vm. Let me check it, then I would explain. It's okay. So let me explain it now. So what we have done, we have a block of certain mass. Let its mass be m. We have placed it on a horizontal surface which is frictionless and attached it to the spring. One end of the spring and other end of the spring is connected to the wall. In let us name these figures. Let this be part A of the figure, part B, part C, and part D. In part A, we have stretched the spring, moved the block to the right, and then we leave the block. What will happen? It will oscillate. So it will have a mean position and it will have two extreme positions. So we have shown x is equal to 0 is mean position, x is equal to plus xm is one extreme position, x equal to minus xm is extreme position on other side, left side in this figure. So when we stretch the spring and leave this block, it will oscillate under the action of the force of the spring, which will be of this form, F is equal to minus kx, where x is the amount by which spring is stretched or compressed from its natural length. When spring is relaxed, force exerted by the spring on the block is 0. When it is stretched, force exerted by the spring will be towards left. When it is compressed in situation C, force will be towards right. So displacement and force are oppositely directed. Here displacement is to the right, force is towards left. Here displacement to the left, force is to the right. So in B and C, spring is relaxed. That relaxed situation corresponds to equilibrium position, because at equilibrium position there is no force on the oscillator. So we have written here F is 0, A is 0. Why A is 0? A stands for acceleration, because Newton's second law says F is equal to ma. So if force is 0, acceleration is also 0. So you need to understand it. At equilibrium position of the simple harmonic oscillator, force on the oscillator is 0 and its acceleration is also 0, as in B and C. Here in part A of the figure, displacement is plus xm, so force will be minus kxm. Why? Because force is minus kx, you have to put for x plus xm. So force is minus kxm. So it is maximum, but it is pointing towards negative x direction, right? Acceleration is similarly directed, because force and acceleration are similarly directed, and it is also maximum, but pointing in the negative x direction. Speed is 0. So at extreme positions of the oscillation, you need to understand it. The oscillator is momentarily at rest. So in situation A and situation C, these are two extreme positions. Speed of the oscillator is 0 in both situations. And at mean position, situation B and situation D, speed of the oscillator is maximum. So when oscillator comes from mean to extreme, speed decreases, and when it comes from extreme to mean, speed increases, and at mean position it becomes maximum, and at extreme position it becomes 0. Oscillator momentarily comes to rest, right? Oh, and you can see here force is towards left, speed is 0. In situation B, there is no force. Oscillator is at mean position, but it will be moving towards left. So there will be speed maximum, but oscillator is going in the negative x direction, it is negative. Compare with situation D, here force is 0, acceleration is 0, velocity is plus Vm, because speed is maximum, but oscillator is moving to the right, right? So this was the explanation of this, and this is true for all particles, all bodies which move in this fashion, that means which are executing simple harmonic motion. These features are same, that at mean position speed is maximum and extreme position speed is 0. So this was an example of simple harmonic motion. A block of mass acted on by a spring of spring constant K and sliding on a frictionless horizontal surface. So now you can understand the meaning of some why there is simple harmonic oscillator. It is a model oscillator. You can understand other oscillations in terms of this oscillator when their amplitude of motion is small. So we can define oscillator in terms of force or in terms of potential energy. And then we plotted force and potential energy of a simple harmonic oscillator. Then we said that the equation for force and potential energy matches that of the spring force and potential energy. So simple harmonic oscillator, if we have a block placed on a horizontal frictionless surface and acted upon by spring and oscillating under the action of this spring, that is example of simple harmonic oscillator. Then we explained its oscillation. Now one last thing, from Newton's second law, law of motion, we know net force on the oscillator is mass times the acceleration, and we can write acceleration as second order derivative of position time function with time, right? Now for simple harmonic motion, there is only one kind of force acting on the oscillator, which is minus kx. So F net is minus kx. There is no other force. When we substitute here, we can write minus kx is m d2x. It is, you know, x of t. I am writing simply x. It is understood. Here it is position as function time. We can write minus kx is m d2x by dt2, second order derivative of position with time, or I can write it this way, d2x by dt2 plus k by m x is 0. We name it as equation 3. Let me encircle it. We've simply done what? I've taken this to right hand side, it will become plus kx. Here it will have be on left side, there will be 0. Then we have written in this form, we have divided by m. So we have second order derivative of position with time plus k by mx equal to 0. This equation 3 is called the equation of motion of simple harmonic oscillator. So this is equation of motion of simple harmonic oscillator. This all for today. Go through it, refresh your ideas of oscillations, which you have already done. I have given you the idea of simple harmonic oscillator once again. Go through your syllabus. Don't waste your time. Go through all the video lectures which I will be sharing with you. And don't forget to subscribe and like my channel. You can also give comments in the comment box. Thank you. God bless you. Assalamu alaikum.